As a reminder, what is an isomer? If I say that two compounds are isomers with respect to one another, what does that tell you about them?
Same chemical formula, different structure.
Right, so now specifically just plain old isomers, all this really denotes is the fact that they have the same molecular formula. So same molecular formula. Now, we have talked already about a specific class of isomers called constitutional isomers. Okay? And so constitutional isomers were those things that had the same molecular formula but differed in the connectivity of atoms, right? So this was different connectivity of atoms. So a nice example of that was, let's say, C4H10. There were two different ways that we could draw this, right? We could draw it with all of the carbons attached to each other, filled in with the hydrogens. Another way that we could draw it, though, was with three of the carbons attached and one of them branching off the middle carbon, right? So again, these are constitutional isomers. They have the same molecular formula, but the atoms are connected differently between the two, okay? Okay, so now this chapter is going to deal with a different type of isomer comparatively to constitutional isomers, right? So we're going to start talking about something called stereoisomers in this chapter. And specifically, stereoisomers are again going to be isomers, right? So we're going to have the same molecular formula, but now we're also going to have the same connectivity of atoms. So everything's going to be connected the exact same. They're going to differ, though, with respect to their arrangement of atoms in three-dimensional space, okay? So stereoisomers, we've got same molecular formula, same constitution, so same connectivity to atoms, but now, again, we're going to differ in our arrangement in three-dimensional space, okay? Okay, so now, what is the kind of first little stereoisomer that we deal with? So with respect to cyclic alkanes, I didn't talk about the fact that there are different stereoisomers with respect to these guys, but now I'm going to introduce that here because we're talking about our nice Stereoisomerism chapter, okay? So now, if I were to look at this guy, right, so let's say that we have this little cyclic alkane up here, up front, okay? And I were to count the number of carbons in my cyclic alkane, I would find that there's 1, 2, 3, 4, 5, 6 carbons. So what would be the parent chain if I was wanting to name this cyclic alkane? 6 carbon ring, what do we call that? 6 is hex, right? So this is a cyclohexane parent. So cyclohexane, okay? What we have drawn here, the way that this is drawn and projected, this is what is called the Haworth projection. I don't focus on the Haworth projection that much, but how would we draw this with respect to our chair structure? Or even if we want to take Haworth and convert it back to bond line, how would we draw this? So yeah, if we wanted to draw the chair, let's say for this guy, for our compound on the left, we would first make our nice little shallow V, right? We would draw down and connect the dots, okay? Now, what is this implying about these methyl groups that are pointing up? Where are they? If they're pointing up, where are we telling you they're at with respect to our chair conformation? So they're both going to be above the plane of the ring, right? So when they're both up, they're both above the plane of the ring. Let's say that we define this carbon as carbon 1, right? And this carbon as carbon 2. And let's say that carbon 1 is going to be right here. Right, so if I want to put my first methyl in the up position at that carbon, where am I going to put it? The axial or the equatorial? The axial position. So I go ahead, we can draw our methyl up, right? So this is our carbon 1. Now as I move to carbon 2, again, this other methyl group is also up, right? So for carbon 2, what is the up position? Is it the axial or is it the equatorial? So axial, if we draw it at carbon 2, is going to go straight down, right? So then what is up with respect to this carbon 2 position? It's the equatorial position, okay? And so we can go ahead and draw this guy out. So we're going to be parallel with this line. We could draw it like that, okay? So this is this molecule right here, where we have both of our two methyl groups in the up position. Both of them are going to be above the plane of the ring, right? And so I can go ahead and make that compound with my little model kit. So if we make this, we'll say that this guy's carbon 1, this guy's carbon 2, right? We're in our nice little chair. We've got our methyl group in our axial position. We've got a methyl group in our equatorial. Both of these are above the plane of the ring, okay? So that's this guy. Now, let's compare it to this guy over here, number 2, right? So this is our number 2 compound. Again, what would be the parent of this compound? What is the parent chain? So again, we have a hexane. We've got 1, 2, 3, 4, 5, 6. It's a cyclic ring structure. So this is again a cyclohexane. Okay. Again, we have a carbon 1 and we have a carbon 2. And what's attached to both of those carbons? We've got a methyl and a hydrogen, right? Methyl and a hydrogen. We've got a methyl and a hydrogen. So are these constitutional isomers? So we have the same chemical formula, right? Do we have the same connectivity of atoms, though? Do we have a methyl attached to carbon 1 and a hydrogen attached to carbon 1 on both of them? Yes, right? Do we have a methyl attached to carbon 2, a hydrogen attached to carbon 2 on both of them? Right, these are not constitutional isomers, but they are not the same compound, okay? If we were to draw the chair projection of this guy, so got this guy, same thing that we did before. Now at carbon 1, what's happening with the methyl? Is it going up or is it going down? It's going up. So if we want to go ahead and define carbon 1 as this guy, then we've got that methyl again in that up position, which is axial at this carbon 1. Now at carbon 2, which is here, we have methyl going down, right? Who is the down position at this carbon? Is it axial or is it equatorial? Axial. It's axial, right? So we can go ahead and draw this guy in the down position. And we can make this compound, right? So now we've got carbon 1 with our methyl in the axial, it's pointing up. We've got carbon 2 with our methyl in the other axial, it's pointing down, okay? Are these two compounds the exact same? So when I question that, what I ask is, are these two compounds superimposable? Meaning, and I'm going to write this out, superimposable, meaning when you overlay these compounds exactly, do you get the same thing, right? So if I do this, take my little guy over here, take my guy here, I overlay these two, this methyl is good, it matches up, but what happens at carbon 2? Do these guys match up exactly the same? No. So is this the same compound? No. Okay, so these are different compounds. They are not constitutional isomers, though. They are stereoisomers, meaning same connectivity of atoms, but now they differ in their arrangement in three-dimensional space. Okay, so these guys are stereoisomers. Okay, so again, if I wanted to name these, right, how would I go about doing that? So both of them are cyclohexane, that's the parent, right? When we name our substituents on the parent, we can start numbering wherever our first substituent is. So here we have a 1 and a 2. What are the two substituents coming off of that 1 and 2 position? Both of those are methyl groups. So then how would we name this? This would be 1, 2 dimethyl, and then cyclohexane. What about this guy over here, which is a different compound? It's not the exact same compound. What do we have? What group do we have coming off the 1 position? We have a methyl, right? What group do we have coming off of the 2 position? We have a methyl, right? So if we name this guy, we would also have 1, 2 dimethyl cyclohexane, right? Which is an issue because these are not the same compound. They are two different compounds. They have the same connectivity of atoms, but we have to denote which one we actually have, okay? And so to do this, to denote whether or not we have both of the methyls in the up position versus one methyl in the up, one methyl in the down, we use what is called Sis Trans Nomenclature, okay? So cis is Greek, I think, or Latin for same. And trans is Latin for different or across or opposite. Okay? So When we're using the cis-trans, we're saying how are these substituents, where are they relative to one another? Are they on the same side of the ring, or are they on opposite sides of the ring, right? So for this first one, where we have the methyl both in the up position, are they on the same side, or are they on the opposite side of the ring? They're on the same, right? So because of that, because these guys are same, this is going to be labeled as cis, right? So this is going to be cis 1,2-dimethylcyclohexane to denote that the methyls are on the same side of the ring, that cis will go in the beginning of the name. And then over here, we've got our methyl here, we've got our methyl here. Where are these relative to one another? Are they on the same side, or are they on opposite sides of the ring? They're on opposite, right? So this guy, we've got opposite, so we would name this guy trans as a result. So this would be trans 1,2-dimethylcyclohexane. And again, we have to include that cis-trans to denote where the actual methyl groups are relative to one another, because these two guys are not the same compound, even though they have the same molecular formula, same connectivity of atoms. Okay, so this is a big idea with respect to the superimposability. If something is superimposable, meaning when you lay it on top of itself or the other thing, you get the exact same thing, it is the same compound, right? So if things are superimposable, that implies that you have an identical compound. If things are non-superimposable, then you have two different molecules, and you have to denote those cis-trans respectively. Okay, so that's the first little bit of stereoisomers, because we've already talked about cyclic alkanes, so we might as well talk about cis-trans there. Another little area where cis-trans comes in is alkenes. Okay, so remember what an alkene is? Alkene with an E-N-E. What does that imply as a functional group?
Double bond.
Double bond. So we're talking about a carbon-carbon double bond. Okay? So it's a similar situation when we have a carbon-carbon double bond, because remember, a double bond is the combination of what type of bond? We get one sigma, and we also get one pi, right? And so with pi bonds, remember we get pi bonds because of this side-on orbital overlap, right? Side-on orbital overlap. It's that overlap that forms the bonds, right? So if we start to rotate this bond, do we get that same orbital overlap with the pi bonds? No. So again, if I tried to rotate this guy this way and rotate this guy this way, we would break that orbital overlap, we would break the bond. Okay, so because of that, we are not allowed free rotation. So no free rotation in double bonds, right? So they're stuck, they can't rotate. Single bonds are allowed to freely rotate, right? Single bonds, you can sit here, we went through all the various conformations for that, okay? Okay, so there is another implication behind the fact that double bonds cannot rotate, right? So for example, let's compare this molecule to this molecule, okay? If we looked at the molecular formula for both of these, what would it be? We would have a carbon, 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 carbon. So we've got carbon 4, 3 hydrogen, so that's 6, 8, hydrogen 8. What about this guy? What would we get? We would get carbon, 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 carbon. So again, 4 carbon, carbon 4, and again we would get 3, 6, 7, 8, hydrogen 8. Okay, so same molecular formula, they're isomers. What about connectivity of atoms? So right now we've got a carbon here that has what groups attached to it? So this guy, we've got a methyl group and a hydrogen. We've got a methyl and a hydrogen. When we move over here, what does this guy have attached to it? Methyl and a hydrogen. What does this guy have attached to it? Methyl and a hydrogen, right? So these are not constitutional isomers, okay? Are they the same compound, though? No. Can I pick this guy up? Can I rotate it and overlay it and get the exact same thing? No. Okay, so they're not the same compound. They're not constitutional isomers, so what are they? Stereoisomers. Okay, so again, these guys are two different things. We cannot overlay them and get the same thing, so we have to again denote that. Using the exact same convention, this cis trans, if we look at this molecule right now and we compare where the two methyl groups are relative to the double bond, relative to each other, are they on the same side of the double bond or are they on opposite sides of the double bond? They're on the same side, right? So if they're same, what would we call this guy? This is cis, whereas this guy, we've got methyl-methyl. Where are they at relative to one another? They're opposite, so we would call this trans, okay? So again, this is another example of stereoisomers. Okay, so what about this guy down here? We have these two fluorines. When we're using the cis trans nomenclature, we're always comparing the same group on one carbon relative to the same group on the other carbon. So when we're comparing these guys, who are we comparing here? We're comparing where the fluorines are relative to one another, right? Because it's the same group that we're comparing. So right now, where are these two fluorines relative to one another? They're in the cis position, right? Over here, who would we be comparing using the cis trans, right? So for this guy, we've got a methyl group attached. We've got, what is this, 1, 2? This is an ethyl group. Over here, we've got a hydrogen, and then what do we have up here? An ethyl, right? So when we're using cis trans, what two groups are we comparing here? They have to be the same on either side of the double bond. We're comparing the two ethyls, right? So here we'd be comparing where the ethyls are relative to one another. Where are they relative to one another? Across or same? Across, right? So they're opposite one another, so this would be trans, right? So when we're looking for cis trans, we're looking to compare the same groups on either side of the double bond. Yes?
What if instead of a hydrogen on one of the sides, it had some other, like maybe it had chlorine or something?
We can't use cis trans. Oh, no, so for this one,
yeah. So
this is the
imagine
chlorine?
instead of that, yeah, it was a chlorine.
we're still comparing where ethyls are relative to one
Okay.
another.
So like the two.
Yeah.
Okay.
It's got to be the same group that you're comparing, or we can't use cis trans nomenclature.
Okay.
And we'll get into that later on. So just as a note, because sometimes it's not super obvious, imagine if you were given a molecule like this and ask, is this cis or trans? Right, so we have a methyl group, we've got our double bond, we've got a fluorine. Who would we be comparing relative to one another for cis trans? Because they have to be the same on either side of the double bond. Right now we've got a methyl versus a fluorine. We can't necessarily compare those two, the two hydrogens, right? So it's not always obvious who that same group is, but here we'd be comparing where the hydrogens are relative to one another. Again, what would that be then? Trans. Okay, all right, so that is a brief introduction to cis-trans stereoisomers. Okay, so we're going to utilize that with a little practice. So I have 3 molecules here, and I want to know whether or not these are cis, whether they're trans, or whether they're neither, right? So we did this in class. Go ahead and give yourself some time to complete all 3 of these, and then I will go over them after a bit. Okay, so I'm going to start with this first molecule to the left. All right, so we have an alkene. This is a carbon-carbon double bond, all right? And when we're looking at cis-trans stereoisomerism and alkenes, we're looking at comparing where the same group is on the other side of the double bond, right? So for example, right now we've got our carbon here, we've got our carbon here. The groups that we have attached are a methyl. We've got attached here an ethyl. These are not the same, all right? So we can't compare where they are relative to one another. Instead, the thing that is the same that we can compare are these 2 hydrogens, right? So we can say, where is this hydrogen on this side of the double bond relative to this hydrogen on the other side of the double bond, right? And if they're on the same side, then, which they are, this is the same side, then that is cis. So this would be a cis stereoisomer. Okay, so then moving over to this guy, we will try to confuse you quite a bit by drawing these various things in the chair conformation. Sometimes it's easier to see if we draw the bond line structure. So I'm going to convert this chair to my cyclohexane in bond line structure. I'm going to say that this guy is going to be, let's say, carbon 1, and this guy's carbon 2, right? And so right now, in carbon 1, we've got an OH group in the axial position, right? And axial is pointing up with respect to the plane of the ring, right? So we have an up, and if we wanted to denote that in our bond line, we would draw that coming out of the board, right? So we'd use a wedge for that. When we move on to carbon 2, down here, the carbon 2 axial position is pointing down, right? So, docs, yeah, that's it. So down is the axial. The group that we're actually interested in, though, is the equatorial position. So if the axial is down here, then the equatorial has to be up above the plane of the ring. So when we draw that on here, we get this guy also in the up position. So this is up, this is up. Because of that, they're both up, meaning they're both on the same side of the ring, which means they're cis with respect to one another. So this would be a cis isomer. And then finally, we come down to this guy, another alkene, right? We've got a carbon here, we've got a carbon here. Again, when we're looking at cis trans, and we're using that convention or that nomenclature, we have to be comparing the same group on opposite sides of the double bond, right? So when we're looking at these groups, we've got a methyl here, we've got a methyl here. Let me use my highlighter. We've got a methyl here, we've got a methyl here, but we've also got a methyl here, right? And so this is a big thing to note. And I didn't mention this before because I like to do an illustration of it, right? This and this that's attached to the same carbon is the same group. So if we drew the opposite stereoisomer of this, right? If we drew this guy, wrong one, wrong stereoisomer, with our double bond here and our methyl group here, right? This is the opposite of this. Note that this and this are actually the same molecule. So same molecule. We could pick this up, so this guy, if you pick it up directly out of the plane and you rotate it, you flip it over like a pancake, and you rotate it, you're going to get the same thing, right? So this is superimposable. And because of that, there is no cis-trans, right? There is no comparison, there is no stereoisomer, right? If we name this, it would be a unique name, and yeah, there is no, I guess, isomerism there, or stereoisomerism, pardon me. So anytime you have the same group on the same carbon, right, that's always going to essentially just wipe out any type of cis-trans stereoisomerism. So this would be a neither. Okay, so that's kind of like just a basic idea about stereoisomers and like what the definition is, right? So we showed you two examples. We showed you cyclic alkanes and whether or not the positioning of the substituents on that were on the same side and opposite sides and how those are different molecules. Same thing with alkenes, right? So again, a stereoisomer is a compound with the same molecular formula, the same connectivity of atoms, but now their spatial arrangement is different. Their three-dimensional arrangement is actually going to differ with respect to one another, okay? So now, that's the basis, right? Now we're going to move into another type of stereoisomer, right, which we're actually going to deal quite a bit with, okay? And before we can do that, we have to introduce you to a concept called chirality, or chiral objects, okay? So this word, let's write chirality, or when I say something is chiral, I want to note how to spell this or how to pronounce it, right? So I know it looks like CHI, and you probably want to say chiral, but it's not. The CHI extends, or it comes from Greek, the Greek letter chi, and so you would pronounce this chiral, okay, or chirality. Okay, so to introduce this idea of chirality, the first thing we have to introduce is this idea that everything has a mirror image. So number one, first thing to note is that everything has a mirror image. Okay? So, for example, let's say that we had a pair of sunglasses, right? So this pair of sunglasses over here, they have the same frames in both of the lenses, or same lenses in the frames. And we say, okay, this pair of sunglasses, what is the mirror image of this pair of sunglasses, right? And so we could project that, imagining there's a mirror, right? And we could project the mirror image onto that, okay? So, again, everything has a mirror image, okay? Now, number two, and this is the most important one, to be chiral, or to be a chiral object, to be chiral, the mirror image of the object has to be non-superimposable on the original object. Posable on original object. So, if you have an object and it's chiral, it is going to have a non-superimposable mirror image, okay? So for example, let's imagine that we have a different pair of sunglasses where we have removed one of the lenses, right? We can again project the mirror image here, right? So we have our mirror image. This is our mirror image of those sunglasses. If we pick this up, so if we pick these guys up and we rotated them around, right, and we laid them back down on the original object, it would not be the same, right? Because it's not the same, then that means it is non-superimposable. Non-superimposable, right? So if you imagine picking these sunglasses up, rotating them 180 degrees, setting them back down on the original object, you're not going to get the same thing, right? Instead, the clear frame is going to lie over on this guy, whereas the darkened frame is going to lie over on this guy, okay? So because of that, they're non-superimposable. If we compare them over here to the glasses with the same lenses in the frames, right? If we pick this up, if we rotated it around and we laid it back down on this, we would get the same thing. Right, so when it's the same, right, same object, same molecule, that is what is said to be superimposable. When you pick it up, and you rotate it around, you lay it back down on the original object, it is the exact same, it is superimposable, okay? Okay, so these are two different examples. We have something that is superimposable, or has a superimposable mirror image. Again, this is our mirror image. And then we have a non-superimposable mirror image, right, and that's the guy on the right. Okay, so again, to be chiral, you have to have a non-superimposable mirror image. So this guy, the guy on our right, is a chiral object, right? It has a non-superimposable mirror image, whereas this guy, the guy on the left, would be called achiral, meaning it's not chiral. And again, a is like non or something in Greek. Okay, so that's the definition of chirality, right? Non-superimposable mirror image. Okay, so there are other things that are also chiral, besides just a weird pair of sunglasses that has a lens removed, right? Chiral, this word, just by itself, chiral, derives from the Greek word for hand, which is chir, I guess. I don't know how to pronounce that, but this means hand in Greek, right? So chiral, or possessing this property of chirality, is also frequently referred to as being handed or having handedness, right? So another good example of something that is chiral are your hands, right? So if you notice, your left hand and your right hand are mirror images of one another. They are the exact mirror with respect to one another. If you try to superimpose them on top of one another, though, they don't superimpose, right? Your left hand lies on your right hand, you're not going to get the superimposition, right? So they are non-superimposable mirror images, meaning that they are chiral. And again, chiral tends to refer to things, or we like to refer to things as having handedness when they have chirality. So we're going to talk now about, because molecules, depending on what they're made up of, have chirality or can potentially possess the property of being chiral, okay? That's going to have really big, important ramifications with respect to kind of pharmacology or drug design, etc. So we're going to go over how to determine whether or not a molecule does have a non-superimposable mirror image, but kind of as a rationale for why this is important. There was a drug back in the 1950s and 1960s called thalidomide, and you can look it up online, so thalidomide. So this was prescribed, again, in the 1950s and 1960s, and the purpose of it was to help pregnant mothers deal with morning sickness, so it was a morning sickness drug. In the original design, the thing that helped with morning sickness was one version of the molecule, right? So morning sickness was one version of the molecule, just denote it here. This molecule did have or did possess the property of chirality though, right? So it did have a non-superimposable. This is, you know, the word non, I just need to like copy paste all the time, I feel like. So this is non-superimposable. It did have a non-superimposable mirror image. And that non-superimposable, we'll call that star, I guess. That non-superimposable mirror image was a different molecule, right? Because what we're going to find with respect to these molecules and possessing chirality are these are going to be stereoisomers of one another, right? So these are going to be molecules that have the same molecular formula, stereoisomers. They have the same molecular formula, they have the same connectivity of atoms, but because they are these non-superimposable mirror images, they actually differ with respect to the arrangement of their atoms in three-dimensional space. Because of that, right, they are different molecules, and they're going to have different characteristics when they actually go into the body and act as these drugs, right? So again, the original molecule, thalidomide, that was prescribed for morning sickness was this guy, but coming along with it was its non-superimposable mirror image, right? And so mothers were taking thalidomide, they're helping battle morning sickness. The problem was with this guy, right? So whatever this guy did in the body, what happened is a lot of these mothers, whenever they finally gave birth to children with these like flipper-like appendages as hands, right? Which is not ideal. Okay, and again, that birth defect was due to the presence of this mirror image of the original molecule that we were super interested in that actually did help with morning sickness, okay? So again, why is this important? Why do we care whether or not molecules have non-superimposable mirror images? Well, because those two molecules are different and they're going to have different properties, and we need to be able to denote that, right? And we need to know what they're going to do before we actually prescribe them to poor morning sick mothers that end up having babies with birth defects, okay? Okay, so if you do look up thalidomide, again, Billy Joel wrote a song back in the day. It's called We Didn't Start the Fire. There is a verse in there where it says something about mothers of thalidomide. This is what it's referring to. And so here is organic chemistry in a Billy Joel song. So congratulations on that. Okay, so then the question is, well, this is the reality, right? We do have molecules. These molecules can potentially possess chirality, right? So we need to know that. How are we going to know whether or not something is chiral? Okay, so now we're going to go over the qualifications for chirality in a molecule. Okay, so in class we did this activity where we had the model kits out, so I'm just going to kind of walk through that if you don't get the chance to be able to do that. One of the big first qualifiers with respect to whether or not something is going to have chirality is whether or not we're dealing specifically with Sp3 hybridized centers. Okay, so our most common Sp3 hybridized center that we deal with, or most common Sp3 hybridized atom that we deal with in a lot of our molecules is carbon, right? And this is tetrahedral carbon, right? So that means that it has 4 bonds, right? So 4 bonds, no, that's not the right word to use. So 4 electron groups, right? I always like to say electron groups. Again, electron groups can be bonds, it can also be lone pairs, right? But again, with respect to carbon with 4 electron groups, it's always carbon that's in the tetrahedral molecular geometries, right? It'd be carbon, let's say this is hydrogen, hydrogen, hydrogen. This guy is our Sp3 hybridized carbon, right? So we're looking for 4 different things or 4 things attached to that carbon, okay? Okay, so now in this activity, I have given you tetrahedral carbon, right? So we have there's a black ball that's supposed to represent carbon. It has 4 holes in it, right? And that 4 holes is in the overall structure, this tetrahedral structure, right? So the first step in this is I tell you to take 1 black ball and I tell you to make 4 bonds to it, and I want all of those bonds to be to the same color, and that same color will be used as white balls, right? So you're supposed to take tetrahedral carbon, connect the bonds, and make all of those bonds to the same color. Those are going to be white balls, okay? Then I wanted you to use the other carbon, the other black ball, to make the mirror image of the original one, right? So now that takes a little bit more of a perspective. So for example, let's say I have a hydrogen. We've got, let's say, this guy coming out at us. So this is going to be on our wedge, and this guy is on our dash. If I make the mirror image of this, right, this guy is the thing that we see first, right? So it would be this guy on the dash. We would have this guy now, this guy on the wedge, right? So this is the mirror of this, and then this guy would be out, and this guy would be out, right? So it's always helpful to imagine a mirror in front, and then what would you see on the opposite side of that mirror? We would see this guy out front, we would see this guy out front, and then these guys would be in the back-ish, okay? Okay, so that's number 1. You're gonna make carbon, 4 white balls attached, and you're gonna make the mirror image. So now, with those 2 molecules, you're gonna take that mirror image, you're gonna pick it up. Can you superimpose it on the original one? The answer to that question should be yes, right? If you pick this guy up, right, and you rotated it around, or you did whatever, you could superimpose this directly onto this, you would get the exact same molecule, okay? Okay, so now, that means if you can superimpose it, that means it's the same compound, okay? So these are the same compounds. We have a superimposable mirror image, so this is not a chiral object, okay? Now, we're gonna take, in number 2, we're gonna replace one of those white balls with a green ball, okay? And so let's say that green do I have green? I should be able to draw these. I kind of have green, okay? So let's say we'll use our black. No. Yep. Okay, so we'll use our black to denote what our model is supposed to look like. So this is going to be our bond. We've got this guy. We've got our wedge going into the board. And so now we're going to use white. So we'll use white for hydrogen, or black for hydrogen, black for hydrogen, black for hydrogen. But now we're going to change one of our white balls to green, and let's say that green is fluorine, okay, something like that, all right? So now same thing. Imagine that there's a mirror, and we're going to do our hydrogen down. So we're projecting this guy. We're going to get a dash to project that fluorine. We've got our wedge here, and then we're going to have our solid line going into the back, right? So this guy's hydrogen, this guy's hydrogen, now this guy is fluorine. Okay, so this is our mirror image of our original molecule, okay? Okay, so again, I would do this with the model kit like we did in class. So now the question is, if we pick this up and we rotate it, can we plop it down on here and get the same molecule? And the answer to that is yes, right? So there's some rotation that's involved, but you can pick this up, rotate it, and superimpose it on the original. So this is still superimposable. So these guys are still the same molecule. Okay, so here we had carbon, tetrahedral carbon, that's our big requirement. We had only one unique group, right? So they were all hydrogens. So hydrogen, 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 one unique group. Here we have tetrahedral carbon, right? Now we have hydrogen, 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 now we also have a fluorine. So here we have two unique groups around our tetrahedral carbon. Okay, so again, with two unique groups, the mirror image, our mirror, is superimposable on the original object. So this is not chiral yet. Okay, so now we're going to do the same thing. We're going to replace one of these hydrogens again, though. So you take off another white ball. We're going to replace it with, let's say, a blue ball, if you can. So let's keep this guy hydrogen, hydrogen. We already had a green, so that's going to be our fluorine. And so now on the wedge, I'm going to go ahead and put, let's say, a chlorine. Okay, so something different. Okay. All right, so again, we're going to imagine that there's a mirror here, and we're going to go ahead and draw the mirror image of this guy. And so we've got this guy coming out. This guy's going to go in. Oh, that's getting soups Uggs. So we've got this, got this guy. Okay, so then this is a hydrogen. This is a hydrogen. This is our fluorine. This is our chlorine. Again, this is our mirror image. This is how we would imagine seeing it. If we pick this up and we rotated it, right? So pick this up. If we rotate it, how would we rotate it? So we would probably flip this end on end. If we did that, we would get the same molecule. So again, this is still superimposable. And I would recommend demonstrating this to yourself, the fact that you can take a molecule, create this mirror image, pick it up, rotate it, and get the exact same thing again, right? So this is still the same compound, okay? Now, at this point in time, we've got 1, 2, 3 unique groups, right? Because we have 2 hydrogens. So this is 3 unique groups around tetrahedral carbon. Still getting superimposability with respect to the mirror image, right? So this is still non-chiral or achiral, okay? So then finally, we're going to take off that last hydrogen. All right, so we've got our original molecule. We'll go ahead and leave this guy's hydrogen. We're going to take off that last hydrogen. Let's make it bromine. We'll make it red. We've still got our fluorine, and we've still got our chlorine here, okay? And now we're going to do dot, 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 dot. We're going to imagine this mirror. We draw the mirror image. We've got hydrogen to that guy, to this guy, to dot, 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 and to the back. We've got our fluorine. We've got our chlorine, we've got our bromine, and we've got our hydrogen. Okay, so again, we've got our mirror image of our original molecule. Now, the question is, if you pick this up, so if you pick this up, and you rotate it, and you can rotate it any way that you want to, and you plop it back down on this guy, are they superimposable? Okay, and again, this is when you should be doing this with a model, because I want you to demonstrate this to yourself. But if you were to do this, if you pick it up, you rotate it, you plop it back down, there is no way that you will get the exact same molecule when you try to overlay it. Okay, so this is when we enter this realm of non-superimposability, non-superimposable. And again, now what do we have around our tetrahedral carbon? We've got one unique group. So we've got a hydrogen, that's one unique group. We've got a fluorine as another, chlorine is another, and bromine is a fourth, right? So 4 unique groups around our Sp3 Hybridized Center. Hybridized Center. 4 unique groups, Sp Hybridized Center. That's when we enter into this realm of the mirror image of the molecule being non-superimposable. So this is our qualification for chirality, right? So this is what's going to make a chiral molecule. This is what's going to determine whether or not there is some sort of non-superimposable mirror image, okay? So again, because these guys are not superimposable, these are not the same molecule. Okay, they are 2 different molecules, and we're going to have to learn how to deal with that and how to actually denote that. Okay, so how do we know whether or not a molecule is going to have Chirality, how do we know whether a molecule is going to be chiral? Do you have an Sp3 hybridized atom, an Sp3 hybridized center that has 4 unique groups around it? If you do, then you will have a chiral molecule. Okay, so just again to hit home on that one more time, what's going to define whether or not a molecule is chiral? Do you have Sp3 hybridized centers? So Sp3 hybridized centers. Again, what that means is, do you have a tetrahedral electron geometry? And for the most part, everything that we deal with respect to these guys, do you have tetrahedral carbon? It doesn't have to be carbon. I should note that, right? There are other Sp3 hybridized centers. Nitrogen, oxygen, those are all Sp3 hybridized, depending on the molecules that we're looking at. But for the most part, this is usually going to be carbon that we're dealing with respect to this Sp3 hybridized center, right? So again, that's qualification number 1. Qualification number 2, there have to be 4 unique groups, right? So what do I mean by unique groups? Let's say that we had something like this, where we had a OH group here, where we had a hydrogen here, where we had a methyl group here on our wedge, so this would be CH3, and then on the dash we had a CH2, or let's actually just draw it in bond line. Let's draw it in a much nicer, prettier manner. We had dash, 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 there, right? So let's also go ahead and get rid of this guy, because who draws methyls at the end of things, okay? So now, when we're looking at our Sp3 hybridized center, right, so we're looking at this guy, right, and we're looking at the groups that are attached around it. We've got an OH group, we've got an H group, those are 2 different things. And then you may be tempted to say, well, this guy's attached to a carbon, and this is a carbon, so that's the same exact thing. But it's not, right? These are 2 different groups that come off of this. This guy is a methyl, and this guy is a 1, 2. This guy is an ethyl group, okay? So this is a Sp3 hybridized carbon, Sp3 hybridized, and there are 4 unique groups around it. That is the qualification for chirality. So this center is chiral, right? It will have a non-superimposable mirror image. Determining whether or not we have a Sp3 hybridized carbon that has 4 unique groups, okay? Now, when we do have an Sp3 hybridized carbon with 4 unique groups, we give that a specific name. We call that a chirality center or a chiral center. And an old name for this that people have stopped using is a stereocenter, okay? So these are all kind of super interchangeable names to denote the fact that you have Sp3 hybridized carbon with 4 unique groups around it, okay? Okay, so let's say that we're looking at this first molecule, okay? And we're looking for a chiral center, right? So if I started, let's say, right here at this carbon, because it's going to be Sp3 hybridized carbon, what different groups are specifically attached to this carbon right now? So we have this guy out here. What would we call this? Methyl. A methyl group out here. What about this guy over here? Let's just say that's, I don't know, some other alkyl chain. Is it different than a methyl? That's the question? Yeah. Yes, right? So this would be some sort of R group here. Now, what's attached to this carbon that's implied right now that we're not drawing? Hydrogen. Hydrogen, right? How many different hydrogens do we have? Right? So now, is this a chiral center? No. No, because we have 1, 2, 3 unique groups, right? We have to have 4 unique groups to actually have a chiral center, okay? So this guy would not be a chiral center because it has 2 hydrogens. That's the same group. It's not unique. Now, if we erase this, because we don't care about that guy, and we move over to this guy, right, this carbon, again, it's Sp3 hybridized. We've got to the left here, this is a methyl group. So we've got a methyl group attached to the left, What about to the right? We've got 1, 2, what would we call that? Ethyl group. Now, we've got a chlorine. What is it doing if it's on the wedge? Is it coming out at us, or is it going into the board? Coming out at us, right? So we've got a chlorine that's coming out at us. That's only 3 groups, though.
We have a hydrogen going, that's a dash.
Right, so what are we not drawing on this molecule right now? Hydrogen, and what does it have to be doing if the chlorine is coming out at us? Hydrogen has to be going into the board, and it's going to be specifically on the dash. Okay, so now if we look at this center, how many unique groups are around that carbon? We've got chlorine, we've got hydrogen, we've got methyl, and we've got ethyl. Even though this is still the same CH, they're different groups. Okay, so then how many different groups do we have? 4, right? So this is a chiral center or a stereocenter because I can't get out of that convention. Okay, so same thing over here. Same thing. We've got an OH that's coming out at us on the wedge, right? To the left, what would we call this guy? So to the left, we've got an ethyl group. To the right, we've got 1, 2, 3, what do we call that? A propyl group. And then again, who are we implying that's always usually never drawn? Hydrogen, and what is hydrogen doing? It's on the dash, it's going into the board. Okay, so again, this is a carbon center with 4 unique groups around it. Okay, this is also a see, I just did it again, stereocenter. It's a chiral center, pardon me. You know, let it go. I try. Okay, so that seems fairly easy, right? You look around, you say, hey, are these different comparatively? What about something like this, right? So again, we've got tetrahedral carbon. We've got it in a ring-like structure now. We've got bromine coming out at us on the wedge. We can also say who's going into the board. On the dash, hydrogen again. Now, is this a stereocenter?
No,
How do you know?
because you have the 2 carbons on either side of the same.
Right. So because this is a ring-like structure, the question that you have to ask yourself is, when I traverse this ring this way, is it any different than when I traverse this ring this way? No, right? So when I go around the ring to the left, I hit a carbon with 2 hydrogens, I hit a carbon with 2 hydrogens, I hit a carbon with 2 hydrogens. When I go around it to the right, do I hit anything different? No. Okay, so because of this, both of these paths are the same. And so this is synonymous with having the same group, the same 2 hydrogens, okay? So for this guy, we would only have 1, 2, and then 3 unique groups. So this is not a chiral center, okay? So not a chiral center. Now, in comparison, what about this final molecule over here? We've got, again, our Sp3 hybridized carbon. We've got bromine on the wedge. We've got hydrogen on the dash. So now as we traverse this in opposite directions with the ring, do we encounter a different path? Yes. So down this way, all it is just carbon, hydrogen, single bonds. When we move through the right, though, what do we hit? We hit a carbon double bond, which is different, okay? So that means that this and this are unique. And so if both of those paths are unique, then how many different unique groups do we have around that carbon? 4. Okay, so that means that this is a chiral center. Okay, so again, we're looking for 4 unique groups around our Sp3 hybridized carbon. Yes.
What if it was like that, but at the very bottom of the hexane there was like an extra, like there was a chlorine or I don't know, like an ethyl or something?
So you're saying like down here there was a chlorine? Yeah. So same thing. If we go this way, first thing we encounter is a CH2, CH2, CHCl. Same exact way, CH2, CH2, CHCl. Are they different depending on the ways that we go?
No.
No. So even if something was down here, it would still be the same group,
But what
right?
if that chlorine was to the right?
Yeah. So if now that chlorine instead was over here, right, or on either side, now we would encounter a CH2, a CHCl, whereas we would encounter a CH2, CH2, CH2. Those are different paths.
So that would be fine.
That would make it unique either way. So that would be 4 different groups. Okay, so now with that, okay, so finally we did some of these in class at the very, very, very end. So right now what we're looking at, we have 4 different molecules, and we're trying to determine whether or not they have stereocenters, or another word for stereocenters is chirality centers, okay? And we've already gone over the qualifications to be a chiral center, right? So we're going to try to employ that definition, those qualifications that we've just learned, okay? So now I'm going to start with my left-hand molecule here. So we're going to start up here, all right? And it can be helpful because right now we've written this, or we've drawn this in the chair conformation. It can be helpful to go ahead and reconvert this back to bond line structure, right? So in bond line structure, we just draw our nice little hexane or cyclohexane ring, right? So we got a nice little pretty hexane. We only have one substituent of this, so the rest of these guys are hydrogen. We can say that this is, we'll say this is carbon 1. Sorry. Right, so now at this position, we've got an OH group, right? And so at this position right now, our axial would be pointed down, right? So this is our axial, which is a hydrogen. And so because of that, because axial is down with this carbon, then this OH that's in the equatorial position, this is up, right? So if we wanted to convert that into our bond line structure, up we always use as our wedge. So we draw our wedge up here with our OH group coming out at us. Okay, so this is kind of like the conversion from chair to bond line. You don't have to do this, but it can kind of help in determining whether or not we have a chiral center. Okay, so now we're looking for a Sp3 hybridized carbon that has 4 unique groups around it, right? So all of these other guys are just hydrogen, hydrogen. So we know that none of these guys are going to qualify. The only one that maybe will be this guy, right? So this guy, we've got an OH that's coming out at us. We've got a hydrogen that's going into the board. So those are 2 unique groups. And so now the question is, okay, is this way around the ring any different than this way around the ring, right? And so when we look at this, we go left, we go right. These 2 paths are the same. We don't encounter any differences whatsoever, right? And so because of that, these are not unique. They are the same group, essentially, right? So if this guy and this guy is the same group, then we only get 3 unique groups for this molecule. So 3 unique groups, at least at this center. And so because of that, this is not chiral. Non-chiral, achiral, we'll say not. Not chiral. Okay? Okay, so this guy, not chiral. Again, because this path and this path is the exact same, so those are the same groups. Now, same thing for this guy. We can go ahead and convert this into bond line. This guy is axial. It's up at this position. Again, we just looked at this guy already. So this OH is also up. So we call this 1 and this 2. And then when we draw this, we can say this is 1 and this is 2. We get OH and we get OH. Both of them are going to be on the wedge because they're both up in the molecule, in the chair conformation, okay? So now, again, we're looking for tetrahedral carbon, all right? 4 bonds to carbon with 4 unique groups around it. So the first one that I come to is this carbon, right? Again, we have our OH on our wedge here, so that's 1 unique group. We've got a hydrogen going into the board, that's another unique group. Now the question is this path around the ring different than this path? And obviously there is a difference here. Over here, the first thing we encounter is a hydrogen and a hydrogen, whereas when we go this way, the first thing we encounter is an OH and a hydrogen, right? So these are two unique paths. Because of that, these are two unique groups. So yes, this one is a chiral center. Chiral center. And same thing for carbon 2, right? We've got our OH, we've got our hydrogen, this is 1, 2. This path is different than this path, right? So because of that, because those paths are different, these are unique groups. And so we get 1, 2, 3, 4 unique groups. So again, this is a chiral center as well. Okay, so you get 2 different chiral centers in that molecule. Okay, so then moving down here, we are looking at a couple different carbons, right? So sometimes they will throw in wedges and dashes to try to confuse you, right? So for example, they've given us a wedge here. So that's like, oh, look, there's unique groups. There's at least 3-dimensionality, right? They've given us a wedge here or a dash here, and they've given us a wedge here, okay? So if we start over here at this carbon, notice that we've got a methyl group. So we'll say this is a methyl group. This is on the wedge. That means that we've got a hydrogen that's on the dash, so that's 1, 2 unique groups. We've got just stuff out here, so a lot of carbon stuff out here. And then down here, what do we have? We have a methyl group, right? So note that we've got a methyl, we've got a methyl. These are not unique. So for this center, it's tempting to say that's a chiral center because they give you the wedge. But because this is a methyl and this is a methyl, this only has 3 unique groups. So 3 unique groups, so this is not a chiral center. Okay, so that means that we move down to this guy, next one in line, right? On this one, we've got a dash, which is a methyl. That means that we've got a wedge, which is a hydrogen. So this is 1, 2 unique groups. If we go this way, this thing out here is an isopropyl group, whereas this thing out here is a sec-butyl group. These are different. Even though it's carbon-carbon, hydrogen stuff, these are still different substituents. These are still different groups. So this is unique, this is unique, this is unique, this is unique. So this is a chiral center. Oh, I shouldn't say a chiral because then you'll think it's not. This is chiral center. And the same thing for this guy. We've got a methyl. We've got a hydrogen on the dash. We've got a 1, 2, an ethyl group out here. And then we've got stuff, right? It's not an ethyl, it's not a methyl, but it's different. And it's a bunch of carbon, hydrogen, just junk, right? So because of that, this is also a chiral center. So in this molecule, we only had 2. If we move over to the final molecule, we'll note, again, the wedge and dashes are trying to kind of indicate something to us. So we've got a wedge dash here. We've got a wedge dash here. I'm ignoring these guys because both of these are Sp2 hybridized centers, Sp2, right? And that is not one of our qualifications for chirality. It has to be Sp3, okay? Okay, so then if I go back to this guy, if we've got a 1, 2 carbon, an ethyl group on the wedge, that means we've got a hydrogen on the dash, we've got a methyl here, and then we've got other stuff, right? So ethyl, methyl, other stuff, and hydrogen. That is 4 unique groups, so this is a chiral center. And then finally with this guy, we've got a methyl group on the dash. We've got a hydrogen on the wedge, so this is 1, 2 groups. We've got other stuff, we'll call this R1, and then we've got other stuff, this is R2. This is another sec-butyl group. R1 and R2 are not the same, so because of that we've got 1, 2, 3, 4 unique groups. So this is also a chiral center. So this guy is also a chiral center. Should have done more colors on that last one, but besides the point. Okay, so we had none here. We had 2 chiral centers here. We had 2 here, 2, and then we also had 2 here.